In this video, we review the basics of complex numbers. Complex numbers are especially suited for describing periodic phenomena. Therefore, they are very important in quantum mechanics, where periodic phenomena are very common. The basis for complex numbers is the imaginary unit. I. It is defined such that its square equals to -1. Of course, I is not a real number. That's why it's called an imaginary. A complex number can be represented by two real numbers. This can be done in two ways. First, the complex number c can be written as a direct sum of a real part and an imaginary part, a plus b times I. A is the real part and b is the imaginary part. Both a and b are real numbers, and I, of course, is the imaginary unit. Second, a complex number c can be written in terms of the magnitudes in the phase with the help of a complex exponential. C equals uppercase A times e to the power of I phi. Uppercase A is the magnitude of the complex number, also called the amplitude, and phi is the phase. Both the magnitude and the phase are real numbers. The phase is given in radians and is an angle. Since complex numbers depend on two real numbers, they can be visualized in a two-dimensional plane. The horizontal axis represents the real part, and the vertical axis represents the imaginary part. The complex number is represented as a vector starting from the origin. Its projection onto the horizontal axis is a real part, A, and a projection onto the vertical axis is the imaginary part, B. The length of the vector represents its magnitude, uppercase A, and the angle of the horizontal axis is phi, its phase. Here are some examples. The number 1 minus 2i can be represented in this complex plane like this. There is 1 unit in the real part and -2 units in the imaginary part, so the vector points this way. Alternatively, if we have given 2 times e to the I times pi over 4, this means that the magnitude of the number is 2, so we first draw a circle of radius 2, and then the angle, the phase angle, is pi over 4, which is 45 degrees, so the vector essentially points this way. Based on this visual representation, we can write down the conversion between the two representations of a complex number. The magnitude A is also denoted. The norm of the complex constant c can be obtained by just squaring A, adding b squared, and taking the square root. The phase is also called the argument, arg, of c. That can be obtained by the arcus tangent of b over a. In the other direction, the conversions are for lowercase a, which is called the real part of the complex number c, that is equal to the magnitude times the cosine of the phase, and b equals the imaginary part of c, and that is equal a times the sine of phi. This way you can convert between the two representations, a in rectangular form and b in exponential form. Most of the time, the second representation in terms of amplitude and phase is more convenient in quantum mechanical calculations.